cell phones, laptops, please. Okay, so we're dealing with doing linear algebra. Still left a lot of linear algebra. So we define this very crucial new idea of an eigenvector and eigenvalue. They come together, as you can see. So it's just a vector that is under the operator. Our operator produces a multiplication. So the linear operators may be complex in nature, by what they do, but this is the simple direction in which nothing is happening but the switch. Okay, so we've seen a few examples, but as a preview of ODEs, why is it that important? So remember what ODE is. It is x, say x prime is equal to ax. That's what we're talking about. So x is a vector, two vector, and a is our linear operator. So if this is 0, then this is what we're talking about. This is my vector x, and that for each vector x, we have a vector ax like this. Okay, so that's what the vector field is. So each location is a vector x, and then at each of the locations, there is a vector attached to it indicating in which direction we are moving and how fast too. Okay, so a velocity. So but then what is so special if we take our vector to be the eigenvector, then it looks especially simple like this. Okay, so in other words, we're moving, look at it, the picture, we're moving straight away from the origin. Okay, so if I'm here, so this is the origin, this is where I am, I'm moving in the exact, or towards it, we could move in any direction. But along, there is no rotational, so we're not getting off that line. So the line on X is not being left. So as if, so in other words, as if there is no force, if it was something mechanical. The force would move it away from the origin, from the direction, okay, as well as it will accelerate our motion here, as you can see, as we gotta see, that's maybe not clear just yet, but along the straight line, if we have follow-on eigenvector, we're gonna demonstrate that whole line with same lambda. Okay, so it's not just one with that vector, but if I pick another vector, say over here, that's in some u, then it once again will be stretched by the same amount. Which what does that mean? There is a very special dynamics within that line. Very special, meaning that there is no deviation, and so like I said, if it's a mechanical, then there is no force because the motion is well, I probably know that's I don't think I want to take this back. So we're not doing forces here. But we're not deviating from direction, which means what? If we have two populations, okay, two populations, then what does that mean? It means that there is as we saw with a predator prey, there is always one is losing, one is gaining. Okay, but this is not it. This is a very special direction because if there is a special combination of the two populations, that doesn't have to be predator prey. It could be just two populations, somewhat they're competing for this, maybe eating each other, maybe they're competing for food, maybe they're actually cooperating in some way. Doesn't matter. All of these are determined by the four numbers of our matrix. And then, but there is a special combination or of the maybe twice as many prey that predators, then that allows us to produce what? Produce a motion along a straight line. And it is actually quite specific what it is, because we end up with x prime is equal to lambda x, v rather, let's say v, that's my eigenvector. And then what the result is exponential. That equation has been solved multiple times. And then, so it means that both of the population proportionally will remain, the proportion of them remains the same, and they will be developing, say every year to double, every year double. So you go in along straight line. So that's the dynamics. The dynamics that is this is generic right here, and this one is special. Okay, so there are special directions that will give us special dynamics for our differential equation. So we're going to see this later in detail, but right now we still just a way to preview where we're heading and why we care. Special directions of the dynamics, and they remember that between these two directions or more, there will be the behavior will be more complicated. But this is some. Okay, so so let's back to linear algebra. And for the eigenvalues of the identity matrix is 1, okay, because it's literally solving the equation lambda b is equal to b. The only way for it to happen when b is not equal to 0, it's not allowed to be equal to 0, is lambda equal to 1. Okay, so all right, so then that's and then every vector once you pick lambda equal to 1, every vector is an eigenvector. So that's as trivial as to guess. This one we worked on from scratch, 2003, and we end up with the trying to figure it out from scratch from the definition. So this is the definition. I'm writing the definition of eigenvector, eigenvalue, lambda need to be found, x and y need to be found, 3 numbers. And it is if we can factor it out because there are a bunch of zeros. So factoring solves the problem, and so 2 equations, either one equation or the other equation have to be satisfied, or well, actually both of them have to be satisfied. The only way for that to happen are these: if lambda is equal to 2, then y has to be equal to 0. Okay, if lambda is equal to 3, then x has to be equal to 0. And therefore, there are 2 directions along the axis that guarantee that this happens, and therefore these are the only directions along which there is a stretching. Okay, so as we know, this is a disproportional stretch, and it's easy to tell that what happens. So in the vertical direction, this is doubles, and here it is triples. Okay, so like that seems to be easy to understand what happens. But then when we start thinking about what happens to other vectors, and such as this, for example, it does not triple. It will become this, right? That's what happens to the vector in between. So it is a complex behavior, and these are 2 simple directions. Okay, so here we have found that because the formula, the operator was so simple. Okay, so the whole x-axis is the horizontal set. They correspond eigenvector corresponding to eigenvalue of 2, corresponding to eigenvalue of 3. That's the vertical line. So once again, the vertical line meaning the y-axis. So once again, the x-axis is stretched by 2, the y-axis is stretched by 3. We knew that, but now we also know that there is nothing else. We have tried to find all the eigenvectors, and we could not. So which means that every other vector will be rotated somewhat. It will be also stretched, but it will also direction will change. That's the picture showed. Okay. So all right. So okay. So that's then you can generalize the idea of what we just got for every diagonal matrix. Once again, H and D with possible flip, which makes no difference really. And once again, 2 disproportional stretches will produce this effect of horizontal and vertical separately being stretched. Okay. So all right. So if any non-zero, that's the crucial things that we have discovered. We are ended up with the whole x-axis and the whole of the y-axis, and then turns out that's not an accident. So our problem that we're trying to solve, find all the eigenvectors, the answer is we find always into many of them. It's not one somewhere. A whole, if you have an eigenvector and you take its non-zero multiples, it's also an eigenvector. Okay, and it happens to be with the same eigenvalue. Very easy to see if you just do some algebra of with these operations. So if this is given, the eigenvector is given, I multiply by k, apply the a to that vector, and end up with proving that exactly once again nothing but stretched by lambda. Okay, so that proves that if we have one eigenvector b, then this is the whole bunch of 0, bunch of all of these are also eigenvalues with the same lambda. Okay, so what we observed over here in the case of vertical and horizontal, it actually applies to all eigenvectors. Okay, so that's called the eigenspace. So eigenspace, you can tell why. So it consists of all multiples of vector b, which is that picture shows right there, and Why is it called eigenspace? So eigen, we know that's just a German. Why do we call it space? What space is it? In what sense is it space? What space have we seen?
Sheet,
Well, like what?
a sheet?
A sheet?
Yeah, like,
Well, yes, but they are, it's everything is straight, remember that. So linear algebra, there is no curving or any kind. So what kind of sheet are you talking about? What?
like a plane?
Well, it could be a plane, but strictly speaking, the first example probably is a line. The first example is a line, and that is a space. What is it? What it looks like? It looks like R, the real line. Okay, so that's the simplest vector space that we can think of. But then the second one is indeed the plane. Okay, so we already had an example of that. The only plane to fit inside the plane is the same plane, but that's nonetheless the case. Here, eigenspaces are two. Okay, so that's the space is R2. The whole space of ours is R2, but there is a lower dimension, which is R1. And we might have two of them as we have over here. And in this case, we have a bunch of eigenvalues, eigenspaces for each of the eigenvalues. Okay, so if we have one eigenvector, we have a whole line of them, but it's also possible that they could create a whole plane. So that idea is really more useful later on in higher dimensions, because then in higher dimensions the space will be in 3 dimensions. For example, you have a line, plane, and the space. Okay, so and then all of the dimensions will be either lines passing through the origin, or planes containing the origin, and then so we have a bunch of subspaces created in this fashion. Within those spaces, as I said, so Y space really it is where the dynamics of our differential equation will be very simple. If we stay within it, and we do, that's the point, we will not be leaving it. Our differential equation will not take us outside. So it's a kind of self-contained dynamics. So it's self-contained in terms of the algebra as well as the differential equations. So it will stay, as I showed on this picture, the the line, we will never leave this line. So if this is my eigen space, this one, E lambda. Our vectors, no matter how many times we apply our linear operators, will stay within it. So that's like a self-contained. That's why the word space is appropriate, because everything stays within it. Okay, so
So what you're saying is the eigenspace tells you the line that the vector exists on,
yeah.
and then you can just kind of move it around on that line.
Well, the linear operator A will be applied again and again and again, but it will never turn it away from that line. So if a vector lies within it, like this, and then that's vector V, okay, and then you apply, where is AV? You ask yourself, and the answer is, well, it might be here, it might be there, but it will never turn. And you can keep applying A, so it is dynamic. So you don't really need differential equations to realize that there's dynamics here. You take one linear operator and then you start applying it again and again and again. You can have a sequence of vectors, but where are they? They are not going in. There's no sequence somewhere going somewhere, and so kind of spiral or anything like that. It will go along a straight line.
Yeah, so the direction can change and the size can change, but it'll never leave that line.
Right. Right, so direction could go, well, let's see, so it will change the direction when lambda is negative, right? It will change the direction every time. Here lambda is negative, then it goes in the opposite direction. When it's positive, it will always go in the same direction, so it will gradually go into infinity along the straight line. Okay, so naturally, if we switch to ODEs, that the dynamics will change slightly, so it will not go one step at a time, it will accelerate exponentially. If it is negative lambda, it will decelerate exponentially, decay towards the Okay, so we'll see that later, but right now, like I said, so the algebra of this linear operator becomes self-contained within that space. Okay, okay, so okay, once again, if you have identity matrix, it's only the only eigenvalue is one, and then every vector is an eigenvector, so which means that the eigenspaces are two. Every vector, nothing happens to it. This vector, as we already did analyze, the E2 is the x-axis, E3 is the y-axis. Okay, two copies of real. So there, once again, as long as we decide on which eigenvalue we want, then we're staying within one line or the other one. For ODEs, let me make a better example here. So, okay, a better example of this is okay, so suppose if this is our linear operator and we're looking at x prime is equal to ax, okay? So once again, pretending that we don't know the answer, and then we run through and find the eigenvectors, and therefore we find the eigenspaces, and then our dynamics will be very simple along those eigenspaces. So it will be doubling on the x-axis and tripling on the y-axis. If that's the case, then they actually can be very easily solved by the means that we know, because that 2 and 3 become the exponent of our function. So look at that, x prime is equal to 2x. That's not a new differential equation, it's one dimensional. And so that's what we expect to happen every time we are dealing with the differential equations, is that if we find eigenvalues, so there will be, if this is there, everything is here. Okay, the first differential equation. If we stay on the x-axis, if we are in the x-axis, we stay in the x-axis. That's the self-contained part. And the other part, if we were to go with the other one, stays here as well. So it never leaves. So the whole dynamics, you don't, even if you don't know what exactly the answer is, it will definitely stay within. And everything else will be complicated. So that's the unfortunate reality. What's happening elsewhere, we don't know. So we just concentrating on the simplest situation. Okay, for the best we can do. The point is, though, is that if we cannot guess, then we need to carry out competition to find the eigenvalues, and maybe it might actually look like this. Okay, so that's the generic case. So what a matrix of an unknown nature with 4 numbers, not necessarily just 2 and 2 zeros. It will have typically have 2 different eigenvectors, 2 different eigenspaces, and then once again there will be dynamics within the blue line, there will be dynamics within the green line, and then something else is happening in between. We already know what roughly can happen. Maybe it might behave like this, maybe. Okay, so well, if I take the generic behavior, maybe like this, we don't know. There's a bunch of possibilities that we have seen, maybe like this. Okay, so remember when we looked at the singular points of systems of 2 dimensions, that's the kind of behavior that you expect, but only when you found directions, the eigendirections, eigenspaces, and then you know what's happening on each of them. In this case, actually, my pictures are not correct, because if the values are positive, so lambda positive, and the other one also positive, which means that both of them are growing, which means that the dynamics will be like this on both of them, like that away, exponential growth in both directions. And then the other solutions will behave in some once again way that is like this, just in a kind of wild possibly manner, but they are running away. You can imagine the behavior could be if I have 2x negative 3y. Okay, so if I had this differential equation, the story would change, because the blue one is still running away like this, but here we have a convergence towards the 0, and that's when the behavior will be like this, like this. So then knowing what's happening on the eigenspaces will tell us what happens elsewhere, at least in a manner that is kind of qualitative, as this is QA, I suppose, what this is. So if we care, but there is no way for us to easily jump to the qualitative analysis without finding these special directions. So we need the algebra to find them, and we're gonna do that next. Okay, so that's the good news, that when we find it, unfortunately, it is quite possible there are no any eigenvectors, and that's rotation. If my vector rotates, my linear operator rotates, then every vector rotates, there are no eigenvalues. No real eigenvalues. So if there are no real eigenvalues, what kind of eigenvalues can we expect? Maybe. Besides real? Complex, yes, so we're gonna do that at the end. We hopefully we have enough time to examine the complex eigenvalues, but for the time being, there will be no this is the good analysis when everything is fine, either going towards the origin, away from the origin, or a combination of the two. But rotation will have no eigenvalues because every vector rotates. Okay, the zero matrix is once again has a zero eigenvalue, which and then every vector is an eigenvector. Okay, but this is the projection. That's where things become that's a kind of singular situation, non-generic. When there is a one direction is really special because there is a collapse along this line. This one is simple; it's a collapse on the x-axis. Sorry, on the y-axis, and then well, what does that mean? It means that everything in the vertical direction will multiply by zero. And if everything is multiplied by zero, that means that the eigenvalue is zero. Okay, and then every vertical vector is an eigenvector. Okay, so you can discover that from the definition which I'm writing here. This is the definition right here. So I substitute my matrix 1 0 0 1, carry out the multiplication. I end up with x equal to lambda x, and at the same time 0 is equal to lambda y, which leaves me with only two possible values for lambda, either 0 or 1. And when lambda is equal to 0, then everything is fine, right? Both of them, both of the equations are satisfied no matter what x is. And if lambda is equal to 1, then y has to be equal to 0. Okay, so that's what we encounter here, which is just said here, and that produces the two eigenspaces. So for the 0, once again, from scratch, I'm doing it in a more roundabout way than we eventually end up doing. But nonetheless, that's a very simple system of equations that needs to be solved very carefully, and because you end up with infinite answers, unfortunately. So if lambda is equal to 0, I plug it in right here. So what do I end up with? Or rather, I'm substituted right here. Okay, so what do I get? Lambda is equal to 0. I have x 0, so that is satisfied. No matter what y is, it is satisfied. And so which means that my vertical vectors, these are the vertical vectors, are all eigenvalues relative to 0. Okay, so vertical collapse, as we knew, but nonetheless, it's we rediscovered through our algebraic analysis. When lambda is equal to 1, once again, I take my system of equations. Both of them have to be satisfied. The first one is satisfied for every x, right? But the second one only works when y is equal to 0, which means that we're concentrating on the horizontal vectors, and all the horizontal vectors are eigenvalues as long as the eigenvectors, as long as the eigenvalue is 1. Okay, so horizontal remains intact while the vertical collapses. We knew that, but now we discovered that with the because it was designed this way. You don't really know if you have randomly numbers thrown around. You don't know the answer ahead of the time. So we are pretending here that we don't know. As if we don't know. We do, but that's because we designed it this way. But generally, you given a matrix with 4 numbers, you're supposed to figure out what it does, and that's how we do it. Analysis step number 1 is find eigenvalues, eigenvectors. So this is another example of we already saw this, but nonetheless, let's just another look at it. How do you find? We know that what this picture shows is a stretch in the one direction along the red direction, and then in the green direction. Okay, so in either way, produces this ellipse. But can you tell? In which direction? If you only know, you can actually see what the operator does. but can you tell which way it is actually stretches in what proportion? And the answer is you cannot. If you delete the lines, you might not be able to find them easily. So then that's where the analysis comes into play. Here it is very clearly shown that for this matrix is the basis vector, the blue one, the purple one. You can see where they end up. Okay, under the operator, they end up pointing in the blue one points in this direction and the purple one in that direction. So clearly they're not multiples of the original. So these are not the eigenvectors. Okay, so they're not parallel. They're not the eigenvectors. So then by the magic that of the algebra that is still to be presented, this is actually Excel spreadsheet. It finds these vectors, the green and red direction. These are the two eigenspaces. These eigenspaces for respectively for the eigenvalues that have been found, and they're here somewhere -3, -2. Okay, and look at it. So the original circles in that's the domain right here. This is the domain, and this is the codomain. And under our operation, as you can see, the circles have been stretched out. Does it tell us anything or not? Maybe not. But look at what has happened to the green ones and what happens to the red ones. They may have been stretched, but they're still parallel. Okay, so these two lines, the green one converges, is transformed into the green one, and the red one is under my operator gives you the red one, which means that vectors within the red one are maybe stretched or flipped, but they're not rotated, which means that these are indeed the two eigenspaces. So these are parallel, and therefore these are the eigenvectors. So the red and green, these are the two eigenspaces for different eigenvalues. And if that's so, that's how we find it. That's how the very simple algebra will tell us how to find these. And you can also decide what if this was a differential equation. So let's quick once again review x prime is equal to ax. Okay, so what is considering that the eigenvalues that have been found are -3, -2, what's the dynamics along these two lines? So if this is u here, say I have that u prime is equal to -3u. Okay, and if I take this one to be v, I have v prime is equal to -2e. That's what. Okay, and then these are very simple differential equations. What dynamics do they produce? Once again, there are no matrices. There are just multiplications. So derivative is proportional to the function. The derivative, literally what those two look like, the derivative is proportional to the vector, to the value. What kind of solution does it have? Exponential. So which one of the two exponential indeed? Which one of the two? Because of the negative? What? Exponential. So these two. What?
Decay.
Decay. Yes, exponential decay indeed. So you can say that then the actual motion will be what? Along the green line, everything goes towards it, as well as along the red line, also everything goes towards it in this manner. Okay, so everything decays. So in other words, if these are two populations, then in that if you combine them in this way, so one population, actually look at it, if you you can actually see it, right? So over here, the green one equal, right? Look at it, it's actually equal proportional. Right, so that line is actually a diagonal line. So when the two populations are combined equally, then they decay at the rate of -3. Okay, and then if I'm not mistaken, and then but if you combine them over here along the red line, which appears to be maybe 2 to 1. Yeah, it is 2 to 1. So this is 2 to 1. Okay, then they also decay, but they did a different rate. Okay, and then the rest of them behave how they also decay, but not in a manner then, so the proportion is not preserved. So that's what's so special about these two lines is that they, as long as you stay within it, the proportion remains the same. So for example, equal population transform over time remains equal proportion remains equal proportion. So that's what the result produces. So and then we find this particular special direction, which is cannot be guessed from my matrix, which I do not see here somewhere. There's my matrix. Here's my matrix over here. This is my matrix, so it has numbers -1, -2, 1, and -4. Okay, so from these numbers, we cannot tell what the dynamics is, but through algebra, we do discover that indeed both eigenvalues, which is -2, -3, and then the eigenvectors, which are the okay. So we just need to learn how to do it. So much so it's so simple that a spreadsheet can do. Okay, so certainly not much of a challenge in comparison, especially to this was a little bit multi-step. No, not too complicated, but nonetheless requires multi-step and kind of a forking analysis. Okay, so no eigenvalues. Once again, this is how you might have no eigenvalues because this is the rotation. Incidentally, if you don't know, then that's how you find out. You go on with once again with the using the definition right here. Substitute. You end up with look at it. So we substitute, cancel out. And this is what I end up with is this. And unless lambda is equal to 0, these two cannot be equal to each other because x squared and -y squared can never equal to each other unless both of them are zeros. And because one is negative, the other one is positive, and so that cannot happen, which means that lambda has got to be equal to 0, but it is not. If we just substitute, realize that that simply does not work out. So then it is there are no eigenvalues, there are no eigenvectors, and then you might guess that that must be a rotation. This is I guess you can say it's a rotation, but it is actually it is a rotation. Yeah, it is a rotation. So you might guess that's a rotation. Okay, so which means that actually matches which means that this dynamics of this might have something to do with the predicate-free model and when you have some kind of cyclical behavior. So we'll get to that. Okay, so how do we do? So let's get to the algebra that straightforwardly will take us to finding eigenvalues, eigenvectors. So all right, so let's just start with an example and simplify our analysis a little bit. So we take that linear operator again, and rather than going with the definition, which is definition here, let's do some algebra. But that algebra, vector algebra. So vector algebra first. Okay, so and as you can see here, can you see what has happened here? I have created a new system. This is my new system with, it is a system of equations over x and y with unspecified lambda. Okay, so it's just the way it's before, but the good news is I have a 0 on the right. Okay, so that is a simple situation, much simpler than what that the original one is. This looks a bit complicated because on the right I have x, y. And remember, when you solve an equation, you want to pull everything you can to the left. And if you're looking for x and y, pull x and y to the left, and whatever is not x and y, leave it on the right. Turns out, so that's the good news. So this turns x, y to the left. Okay, turns out that's the good news. So that's the quite discovery. Right hand side is 0. Okay, so that's the good news because it's a very simple equation that we're looking for, speaking algebraically, is that a certain new linear operator, that we have given by this matrix that we are seeing here. That's this is the matrix. Here's we'll derive what it is. And that the new linear operator actually has got to hit 0 in order for us to find the eigenvectors. Okay, so we are looking for those x's that taken by G, this linear operator, and not F. So this not A. Okay, taken to 0. Okay, so in other words, It is literally what vector is being collapsed to zero. Okay, so it's the analysis is simpler than the analysis of A itself, which is supposed to preserve this. This is the original analysis. So this is better and simpler than what we have done so far. Okay, so what is the matrix of the new operator? Here it is. So once again, the original matrix is over there, and this is the new one. And the difference is negligible, not negligible, but the lambda is brought from the right-hand side to the left-hand side, and what it produced is negative lambda over there. Okay, so that's the difference is, once again, if I, once again, A at the top, and here you can see what has happened. Negative lambda, it's exactly the same except for these two negative lambdas. Okay, so that's the new operator, and that's the one we need to resolve, and it's very simple analysis then to find out for which values go to zero. And the answer is so that this is so we have a linear operator. Let's formalize this. G, that's supposed to be a projection. Okay. So in order to collapse to zero, at least one of the vectors have to be equal to zero. If it's not a projection, there are no eigenvectors. So here's the answer. So A is A, B, C, D, as always. Every pair of an eigenvalue and an eigenvector, lambda and V, of A satisfy the following matrix equation. GV is equal to zero, where G is given by this new matrix produced directly from the original. So that's the original. We add negative lambda, we have a new operator, and then the equation that needs to be solved is really simple. Okay, so that is an indirect. So this is just a stepping stone. Really, it does not really provide us with the answer. How do we find? We still need to find A, B, C, D. No, I'm sorry. We need to find what? We need to find V. So V is still unknown, which is made of X, Y again. So it's still unknown, and lambda is unknown. Okay, so the trick turns out to be is forget about V for a moment and concentrate on lambda. Rather than trying to find them all at once, three numbers, let's find lambda first, and then X, Y would be much easier to find. Okay, so the question then, if that's the case, then what we're supposed to see here is that is a projection. So G depends on lambda, okay, and every lambda is in play, and we need to find which one will do what, which will be a projection. So for the question become for which lambdas is G a projection, meaning that it's not a rotation, it's not a stretch, but there are vectors that collapse to zero. Okay, and the answer is actually very simple, because we have a theorem about that. Because being a projection means what? Not one-to-one, or onto, for that matter. That's what a projection is. Okay. So a vector collapse, you know, remember the linear operator takes 0 to 0. If there is another vector that also goes to 0, that literally means that we have a not one-to-one function. Okay, so okay, so what tool did we use to determine whether or not linear operator is one-to-one? The answer is in the question. Should I repeat the question?
Yeah.
Well, what determines whether an operator is one-to-one or not? The answer is in the question. Should I emphasize with my voice the answer to the question, or even it is a short question? So whether G is 1-to-1. From a long time ago. The answer is in the question. Have to underline. I have to underline the word. That is the answer. What is it? Whether, is it what, is it G, or is it this word? The determinant is the answer, yes. The determinant determines, that's why it's called whether a function is 1-to-1 or not. Okay, so, all right, so how does it determine, if anybody remembers, how does the determinant determine whether the function is 1-to-1 or not?
Isn't it for the determinant 0?
Determinant is or is not equal to 0, correct? So you just have to remember correctly which one is with you. When it is equal to 0 is when it is not 1-to-1. Okay, so it's not 1-to-1, and therefore, so yeah, it's right here. The system has a non-zero solution, or G is not 1-to-1. So we actually remember that being 1-to-1 is good, and being not 1-to-1 is bad, but we are really after not 1-to-1. We want a bad one. G has got to be bad for us to find the vector of the eigenvectors. It has to be bad in that sense. And so for what values of lambda is G bad as in not 1-to-1, and it is the one with the determinant equal to 0. So that gives us, without finding eigenvectors, we can actually tell whether or not the G, that new linear operator, whether or not it is not 1-to-1. So determinant equal to 0, so G is not 1-to-1, which means there is a vector somewhere which goes in non-zero vector that goes to 0. Okay, so that's the one we want. Okay, so that's the condition for lambda. There is no xy for the vector v. We set it aside for now. We concentrate entirely on eigenvalues only, and it is the solution to this equation. Determinant of 2x2 determinant equal to 0 with those lambda. So in other words, what's inside of the parenthesis, so inside the bottom is an equation with respect to lambda. Okay, so it's not too complicated because here's let's run it out. So once again, this step is very easy. I just add negative lambda minus lambda 2 on the main diagonal, take the determinant, and I end up with, as one would expect, a quadratic equation. Okay, quadratic equation, lambda squared plus 5 lambda plus 6 equals 0. Okay, and so all we have to do just to solve it, we have how do we solve quadratic equations?
Foiling,
What?
foil, like that.
For maybe, yes, frankly never learned to do it. For me, the answer always has been the quadratic formula, because I remember the quadratic formula, so we just use the quadratic formula, it works every time. Okay, so, okay, everybody remembers the quadratic formula, you better. So
Minus b plus or minus
minus b, which is what?
minus
Minus 5, okay,
Plus minus.
plus or minus, square root,
square root of 1 b. Oh wait, no, b squared 25
25,
minus 4ac.
4 times 6 over 2. Okay, so let's see, -5 plus or minus square root of 1, is it? Of 1 over 2, so it is 5 plus or minus 1 over 2, which is 3 and 2, is it? Okay. That's it. So the problem that's been solved, and it's so simple that the formula is also available. You cannot ask, I don't think, or not easily, you cannot ask your computer to do FOIL, but you surely can ask it to do the quadratic formula. That's what I asked it to do right here with the same problem right here. So this is the part right here. So the matrix is given, and then this is the quadratic formula gives me the two eigenvalues by the simple computation. So I can change in that spreadsheet. I could change the numbers on the left, and it will automatically produce the eigenvalues for me to in that column over there. Okay, so it is as simple as it looks. It is as simple as it looks. Okay, so it is a quadratic formula, and the numbers just fall in your lap. So so we do not have, to be clear, we do not have the eigenvectors, but nonetheless, if you were to having eigenvalues, it's still helpful because especially if it was ODEs, remember, if it was ODEs, we know that the positive eigenvalues give me exponential growth. Negative give me exponential decay. Okay, so just having the eigenvalues is already helpful. Okay. Even though you don't know what are those special directions, we don't know from this, but we do know that there will be decay. It's not entirely. I can see a bunch of minuses over there, so you can you start thinking maybe a bunch of minuses is it decay or something else, and we just don't know. But now you do. The answer is no. It is actually exponential growth. Okay, so if I were to do ODEs. Okay. So, all right, so let's to summarize, it is rather than dealing with matrix equations and vector algebra, instead is entirely a quadratic equation to be solved. Okay, so it's called that polynomial is called a characteristic polynomial, which is incidentally the same as eigen in German, eigen polynomial, if you like. So that's the algebra here, the German language here. Okay, so once again, as you can see, that's what it is. Chi sub A, so A stands for for the name of the linear operator, and then followed by the determinant of this new matrix. Now, not the same as you can see the matrix of the operators here, and this one is with lambdas. So then the determinant of the original one is a number, and this one is not a number because it depends on lambda, which makes it a polynomial. And then if we set it equal to 0, we end up with what we call the characteristic equation, which is to be solved. Okay, so the good news is, well, if there are certain simplifications, if you will, so I think this is easy to remember. If you were to do eigenvalues, just insert, you have the matrix, insert negative lambdas twice, and then take the determinant, which is really easy to compute. But if you were to explore a little bit more, then you can actually, that's a little bit of a shortcut here. A minus lambda, d minus lambda minus bc is equal to 0. So that's the quadratic equation we're dealing with. We can go straight to the solution, which we already did over here. But every time, no matter what you do, no matter what numbers you insert in your linear operator, you end up with the quadratic equation. And that's here's another couple of examples of what the projection produced, what we discovered in a more complex manner. We discover now the eigenvalues from the characteristic equation, which is frequently very simple, so that we don't really need the quadratic formula. Okay, rotation. Now that's for us to worry about. We already saw this is a rotation. Look at the characteristic polynomial and the characteristic equation. Lambda squared plus 1 is equal to 0. What can you say about this equation? It is a high school information. So lambda squared plus 1 equal to 0. What can you say about the solutions? What?
Like they have I in them, like they're not.
Right, well, yeah, so well, let's suppose that complex numbers are not part of the high school curriculum. So so within the real numbers, the answer is what?
Something like this.
Correct. No solution. So we already knew that, and if we remember where the problem comes from, there are no eigenvectors because rotation rotates every vector, so there are no multiples. But it is important to know that indeed there is no solution. The quadratic equation has no solution here, and And that is the why, and we still want to figure it out. And so that is the motivation for reducing complex numbers. Okay, so we'll have some time for that. And so indeed that if you were to go, then if you have seen complex numbers before, then I is plus or minus I, as a matter of fact, are the solutions. And but they what do they do? Think about it. You have a vector. Okay, if these are my eigenvalues, what can possibly be the meaning of it? You have a vector, say 1, 1, okay, and then you multiply it by I. What effect does that have? It is you are moving from everything becomes complex, not just eigenvalues, but the whole thing is you're moving from the realm of real numbers to the realm of complex numbers. So everything what we have done up until now, including calculus, would have to be translated in the language of complex numbers. So imagine calculus done with complex numbers. Okay, so that's roughly what it would take to use the to proceed from this point on and make a sense of it. So we'll not do that for the time being. So let's just stick to the real numbers, and then it will say, well, if there are no eigenvalues, means that there is some kind of rotation there. So every vector is rotated, so that's what it is. So quickly analyze to refresh your memory about the quadratic formula. Here it is. Fortunately, we're gonna every time, I'm not gonna do a squared ax squared with bx plus c, because the first coefficient is 1 every time with our characteristic polynomial, so it looks slightly simpler. So negative p over 2 plus or minus p squared minus 4q over 2. Plus or minus very clearly indicates where so we have two numbers, unless the determinant, remember the determinant, there is a discriminant, the discriminant, I'm sorry, discriminant, there is a determinant, there is discriminant, because determinant determines, the discriminant discriminates. So it discriminates between the equations that have solutions and those that do not have solutions. Okay, so then how that happens is this. So your quadratic function either lies lies on both sides of the x-axis, or it lies entirely above the x-axis, and in which case you have no solution in the latter case. But it's also a possibility in the transition, the edge case is d is equal to 0 when there is only one solution. So it's a special situation. So also for us to worry about in the case of differential equations. So we have resolved this one is very clear. You have two distinct, the green one, two distinct eigenvalues, and so there will be two distinct eigenvectors, and therefore the behavior will be very much, we already know what's going to happen. So there will be either both converging, both diverging, or one diverging, one converges, but otherwise everything is exponential. So this will be for ODEs, the answer will be exponential. Which one out of the four options there will be here? So negative numbers, this is probably some kind of rotation. Not necessarily rotation, but it has a rotation. Okay, so which means that there will be some kind of we cannot assume that it will come back exactly to the same location, like with the predator-prey model, but there will be some kind of rotation. So it's possible that it might be a spiral rather than just a cycle. Okay, so this is if we look at what it does, it's as you can see, the difference is that the quadratic graph of the quadratic polynomial, the parabola is shifted in the vertical direction, and then the number of solutions changes from 2 to 1 to 0. Okay, so the eigenvalues are the roots of the quadratic characteristic polynomial. The bad news is in high dimensions, if you have 3 variables, you have a cubic polynomial, unfortunately, you have to solve it. And then you have more variables, more degree of the polynomial goes up, and then you run out of formulas. So there's a quadratic formula, there's a cubic formula, there's a quartic formula, there is no quintic formula, unfortunately. So that's the problem. So we are in a good place when the quadratic formula solves this very basically high school algebra solves the problem of differential equations for you in a very effective way. Still missing the complex roots, but nonetheless. So the number of eigenvalues is 2, counting the multiplicities. So that's when in the middle, that's multiplicity 2. So and then so that's a special case. be considered. So there is such a thing as trace. So if you want to another shortcuts, that's the trace is just the sum of the diagonal elements. And you can see if you expand your characteristic polynomial, the formula becomes kind of interesting. So actually, the two coefficients that P and Q that we care about is actually negative trace of the matrix or the original matrix, as well as the determinant of the matrix also makes an appearance. Okay, so that's also interesting, and also reemerges in high dimensions as a shortcut. Okay, so how much we care about that, maybe not a lot, but it is. I put it forward nonetheless, just in case. So that's once again the simplified characteristic polynomial of a matrix takes this form. If you know what the trace is and what the determinant is, they emerge as coefficients of our quadratic polynomial, characteristic polynomial. And then when you apply the quadratic formula, they also appear there. Okay, so as you can see, the determinant actually, if you think about what does determinant do, the coefficient without lambda, it shifts up down, shifts the graph of the function up down, and so it can create two or no solution. Okay, so this is the classification for best we can tell. So there are three cases: determinant positive, discriminant D is positive, 0 or negative. So when the discriminant is positive, there are two distinct eigenvalues, and then the operator non-uniformly, because they're distinct, then the stretches are non-uniform. Okay, non-uniform, and in the distinct directions of the corresponding eigenvectors. Okay, so D is equal to 0, eigenvalues are equal. So it's not that the end there's only one answer. We interpret it in a more advanced way, and so this picture in the middle actually seems like there's only one answer, but actually we say there are two. They just each counted. If there are two, and then one solution counted twice, and therefore there are actually two eigenvalues in a sense. And that produces a classification. This H case in the middle is there is a uniform stretch. Okay, unless that's the caveat here for us to worry about. Unless the eigenvectors are multiples of each other, that's a special case. A special case of the special case. But otherwise, it's a very nice possibility is when the operator expands, which means that your differential equation will be what will be also kind of an explosion that we saw, or rather what a fountain. Remember, if you want to illustrate among ODEs, a fountain. Remember the fountain when everything flows from the fountain on a cone, possibly, and accelerates down. Okay, so that would be if the two eigenvalues are positive. Okay, so then there is acceleration, and then there is the third one. That's definitely is not no. The third one is no fountain, because there is a, well, it could be still fountain, but I don't think you can. What would make water on flowing down a fountain to make it go kind in a manner that is spiral? Okay, so this a possibility, either a full rotation, or it is possibly a spiral like this, away or towards the center. So the behaviors are still very complex, and still this one is the simplest case when two distinct eigenvalues, the non-uniform stretch, and then there is once again some kind of flow, but with the turning, there will be turning of the trajectories of those objects, although the flow. The only case when it's possible that it looks like a fountain is when D is equal to 0, and which means that eigenvalues are equal. Okay, so that best I can do for now without looking into actual eigenvectors. So we'll do better. Okay, so we continue on with this classification of linear operators according to their eigenvalues, which is what we saw, but we can do that. It's less about, so we'll get to the classification again, but how do we find the rest of them? turns out that's really good news, is that solving the ODE within each of the equations, which in the eigenspaces, produce the rest of the solutions too. Okay, so it's not like we have to guess what's happening in between. So we know what's happening here, say like this, and then we don't know what happens elsewhere. It's not true, actually, because why so? Because of the how do I explain it? Because if there are two distinct eigenvectors with two distinct eigenvalues with two distinct eigenspaces, then the eigenvalues serve as a basis. Okay, so the rest of, if these are my vectors v1, v2, every other vector is expressed as linear combination of these. Okay, so if that's the case, then we can also find the representation for wherever the vectors go of these. So here it is. Okay, so let's just read it out. So we have two eigenvectors of linear operators that corresponds to two possibly equal, so it's case 1 and 2. Okay, eigenvalues lambda 1, lambda 2. Okay, so it's case 1 and 2. Discriminant is either positive or equal to 0. Okay, so and then suppose v1, v2 aren't multiples of each other. Okay, so they look like that picture up there. Okay, so then the behavior on the lines is clear. So here is what's my function is f. Why is it f? Okay, f v1 is equal to lambda 1 v1, and the other one is that. So that's along this line. Along this line, what's happening is f v2 is equal to lambda 2 v2. Okay, so once again, everything is clear. What's happening around those two lines, but then what happens elsewhere? Easy, really easy. Every vector, look at the picture, every vector on the plane can be expressed as a linear combination of v1, v2. Because they are distinct and they're not multiples of each other, which means that they remember if we look at the linear combinations of those two, because of the lack of redundancy, they cover the whole plane. And so every vector can be expressed as a linear combination, R1 v1 plus R2 v2, all these two vectors, and then we simply apply the linear operator to vector x, and then look at it. What happens? Well, there's an equation here. We have been able to, because of the linearity of that, we are able to factor it out. Maybe I'll write it out. So f of R1 v1 plus R2 v2. Okay, so I'm using linearity, which means that I can factor everything out. It will be R1 f of v1 plus R2 f of v2. That's nothing but definition of linearity. Okay, so everything is simple. So you can factor everything out, and I'm factoring out both addition as well as scale multiplication. And then I just use the, because I know that v1 is a linear operator, I'm sorry, is an eigenvalue. So it will be lambda 1 v1, and then the second one, v2, is also an eigenvector, but with a different eigenvalue, so lambda 2 v2. Okay, so then I have found everything. I have found the values, the outputs of every vector is known now. So that's the thing about it. Remember that when we talked about linear operators and how do we build a linear operator, how to define its matrix, and the answer was just look where the unit vectors go, the basis vector go. Okay, so that was sufficient. So matrix of f, how where the bases go, and so such as f of e1, that's the first column, f of e2 is the second column, and then you combine them together, produce your matrix. Okay, remember this? And so we are in a similar place, except we're not looking at the standard basis, we're looking at the non-standard basis in a way that has been discovered. That applies to this particular linear operator, but nonetheless, the picture is very similar in the sense of these are E1, E2. Okay, but instead, this is what they look like. So you wanted to, like, they're perpendicular, they unit vectors and on. That's not the case anymore, but that's okay because there is no redundancy. And then if you start looking at linear combination, you get the whole plane. And in that case, it doesn't matter. Once again, the knowledge of these, I put parentheses here just to make my point. So this is sufficient. Just as this was sufficient. Okay, so this was sufficient. To find the whole matrix, the whole operator, you just need to know where the basis vectors go. Okay, so that's how we started, and now we're in a similar place, but we're not looking at the standard basis, but we're looking at the eigenvectors. And once again, if we know where the eigenvectors go, and we do, if we found the eigenvalues, then we are, once again, it's sufficient. It is sufficient. The only problem is when that plan fails, if the two eigenvectors are actually happens to be multiples of each other, so the plan falls apart, unfortunately. But let's suppose we are lucky, and that edge case is not what we're dealing with. So the eigenvalues are actually distinct and not multiples of each other. So then we can express every vector in terms of the eigenvectors, and then the formula is that comes out is this. Okay, so once again, two eigenvectors and their respective eigenvalues, and then so we know where x goes under these circumstances. So so for example, let's take a look at this. So this is my system on the left, the matrix on the right. The computation has been carried out by the spreadsheet behind the scenes. So everything is found for us. So let's review it anyway. We create the our characteristic polynomial, -5 lambda plus 6. Okay, so we quadratic formulas produce -3, -2. Okay, so which is not, you cannot guess it from the picture, by the way. And then the eigenvalues, eigenvectors are also found. Okay, so we actually, how do we find the eigenvectors? So this is, so we already explained this part. And now we need to explain the other part. So this one is done. And this is next. We need to explain how from the eigenvalues, -3, -2, that simple quadratic formula, how we will produce automatically. We tell the computer how to do it to produce the eigenvectors. Okay, so where did these two green and red line came from? It's done by the spreadsheet. The answer is not too complicated because we need to find 3, and we already found one of the 3 unknown numbers. So here I take -3 first. Okay, so -3 first. I substitute the definition. This is my definition of eigenvalues. Okay, substitute here, and simplification produces very simple produces invariably. That's what might get simpler if we already know what lambda is. We end up with 2 identical equations. Okay. You can check. So once again, the equation is here. That's a matrix equation, and then I spread it out, expand it, and I end up, when I simplify, these are 2 identical. And so, in fact, there is one equation, which means that, well, what does that mean? What's the meaning of x equal 1? We try to find xy that's our hypothetical eigenvector is xy. We found that x is equal to y, so what does it mean? Well, that is a restriction, the only restriction on the eigenvector. That the first coordinate has to be equal to the second component. The first component equal to the second component. You see it here. What is it? On the left.
So green.
The green line, correct. The green line, correct. It goes diagonally. So x is equal to y. So we have found one of the eigenspaces, the green one. Okay, so just pick up where I stopped next time. Thank you. Let's see.